Okay, so these are the notes on enthalpy. It's another new science term that we're introducing here, and I know a lot of them are sort of strange, random words to you, but hopefully you'll get used to them as we go on. So just to start off with, we're going to review what we've been talking about thus far this unit. You can see here that we've been talking about heat and thermal energy and all these things related to like the motion of particles and kinetic energy. So that's been pretty much the focus of the unit thus far. So with the calorimetry and the Q equals mc delta T, that's all talking about heat and temperature and thermal energy and kinetic energy, which is the motion of particles and whatnot. When we're moving on to talking about enthalpy, what we're going to be talking about here is the potential energy that a chemical has. Okay, the potential energy that's held within its bond or within the pressure that it has. And just to think about it, it should make sense to you hopefully that if something has high pressure, it has higher potential energy stored up in it, because if you do something like, say, if you had a container and it was highly pressurized and you took it and you struck it with a hammer, it might burst and explode and release a lot of that energy that it has stored up in it. So enthalpy is going to be dealing a lot with how much energy is stored inside of a chemical and its bonds and its pressure and its volume. However, I'll tell you, we're mostly going to focus on the bonds because you'll see later on the pressure and the volume tend to be pretty stable over time. So, as I said, this stored energy is called enthalpy. That's the energy that's stored up within a chemical. The symbol that we use for that is H. I know this is kind of confusing. It's another variable, this unit, that it seems like it's mismatched. We had heat was Q. Now we have enthalpy, and that's H. And you might wonder why heat wasn't H. Well, I have no idea. It's just some crazy thing that chemists did. So enthalpy, that's H. And then if we're looking at a change in enthalpy over time, you can think of that as the difference in energy between the reactants and the products, and I'll discuss more about that here pretty soon. Here's something else with enthalpy. As I said, that it's the stored energy in a chemical, and it relates to bond energy, but also pressure and volume. Well, assuming that the pressure in a reaction is held constant, which is actually the case for most reactions that we do because they're exposed to the outside atmosphere. So if you're doing a reaction in the lab, the pressure is not going to change really because you're not going to change the pressure of the entire atmosphere. So assuming pressure is held constant, we have this relationship where the enthalpy change, delta H, is equal to the heat of the reaction. Now what I mean here is if you have a change in stored energy within a set of molecules, if say the stored energy goes down, well, because of the law of conservation of energy, energy has to be conserved. So if the stored energy goes down, then it needs to release some energy to the environment, and it would release that as heat. So generally speaking, if the pressure of a reaction is constant, then the change in enthalpy is going to equal the heat. Here's another way of calculating change in enthalpy, is just the products minus the reactants. Remember that delta always means change, and it's final minus initial. So it should make sense to you that in a reaction, the products are what you end up with. That's your final enthalpy, and the reactants are what you start with. That's your initial enthalpy, so delta is final minus initial. So here I'm going to show you an example with bonds just to help you understand how this works. I'll tell you, I'm not going to test you on this part of it. I just want you to know what enthalpy means and how it kind of makes sense. So what we've got here is a combustion reaction for methane gas. I'm going to go ahead and put in the Lewis structures for these different molecules. So you can see there we've got the methane here, and it has 4 of these carbon-hydrogen single bonds. All right, and then we've got 2 oxygens. Each oxygen has a double bond, okay, an oxygen-oxygen double bond. So we'll be breaking 2 oxygen-oxygen double bonds here. And what's formed here, the bonds that are going to be forming, are 2 oxygen-carbon double bonds and 2 oxygen-hydrogen single bonds for each of these waters. Okay, so a total of 4 oxygen-hydrogen single bonds. So you see that just summarized down here, 4 carbon-hydrogen bonds broken, 2 oxygen double bonds broken. Formed we have 2 carbon-oxygen double bonds and 4 oxygen-hydrogen single bonds. So if you look at this table of bond energies, you'll see that each type of bond has a special energy associated with it. So we can look here and we can see carbon-hydrogen is 413 kilojoules per mole. When it says per mole here, for now you can just kind of consider that per mole of methane. Okay, so coming down here, we see oxygen-oxygen double bond at the bottom. All right, and then we have carbon-oxygen double bond right above it. Okay, and then oxygen-hydrogen bond is going to be over here. It's 464. So if we take all of those and you say breaking bonds is going to require energy. Okay, it always takes energy to break a bond, to pull some atoms apart that want to be together. And then when a new bond is formed, chemical actually releases energy. This might seem a little bit weird, but think of it this way. You have two things and they're being attracted to one another. When you let them go, there's some potential energy that exists between them. So when they get closer together, they're losing that potential energy that they had to move closer together, and they're releasing it, usually as heat. Okay, so the bonds formed in this case are going to release 3,466 kilojoules per mole of methane combusted. And if you can see this, this requires less energy than it releases. So we should have a net release of energy here. So what we get if you bring those numbers together is that the enthalpy change for methane gas upon combustion is negative 818 kilojoules per mole. Now remember, negative with Q is exothermic. So this is a combustion reaction. It's burning methane. It's just like what you would do in the lab with your Bunsen burners. Bunsen burners release methane gas. So when your Bunsen burners are releasing methane gas and you're burning it, it's releasing a lot of energy. So 818 kilojoules per mole of energy, in fact. So now we're going to review here some things and talk about how endothermic and exothermic words describe things with enthalpy. It's very similar to what we talked about with heat, so it shouldn't be too crazy here. So what we've got here is an endothermic reaction. Remember, endo means heat is going into the system. It says energy is absorbed during the reaction. Okay, so if energy is absorbed, then the enthalpy is going to increase between the products and the reactants. So the products are going to have more enthalpy than the reactants do. So delta H in this case is going to be positive. And as you can see, yeah, this is just some review from what we talked about with heat, but now we're talking about it in the context of enthalpy. So exothermic reactions, just the opposite. Energy is going to be released because exothermic means heat is leaving. So that means the products are going to have less enthalpy than the reactants did, which means delta H is negative. And again, this is just sort of a review from before. So now I'm going to give you sort of a diagram or a chart representation of this. If you look at this, you can see we've got the energy, which you can consider the internal energy or the enthalpy of the products at 50 and the reactants are at 37. So you can see here, this is endothermic because products have more than the reactants. So if we do delta H here, we get a positive 13 joules because it's, again, it's products minus reactants. 50 minus 37 is 13. So it is endothermic. Okay. The way we can write this is representing a chemical equation. Reactants yield the products. And then what this is just showing is if you wrote out a chemical equation, at the end you'd write delta H and then how much energy is produced per mole of the reaction that happens. And we'll talk about that more when we go through your enthalpy practice worksheet. And then just as a last thing, you can see over time, the energy or the enthalpy is going to go up. So what we'll do is we'll have a positive slope there for that graph. Exothermic is exactly the opposite. So let's say we have some reactants and they're starting at 37 joules. Um, the products only have 12, so energy is lost or given off. In this process, the system loses energy. So delta H is going to be negative. Okay, you would write this again just the same way, a chemical equation, reactants yield the products, and then delta H equals negative 25 per mole of the reaction that happens, and that has a negative slope. Okay, so I'm going to introduce how to do the stoichiometry problems with this, and then when it comes time to look at the practice problems that are at the bottom of your page, just go find the video for the enthalpy practice worksheet, and those first two problems that are on, or sorry, I think they're three. The first three problems that are on the bottom of your enthalpy notes will be on the video key for that assignment. So just find the enthalpy practice assignment, and I'll go through these. But the process, generally speaking, as I said, we're bringing back stoichiometry for this. So same first steps as stoichiometry. First, balance the equation. Then start with what you're given in a reaction. So that's where we find the number that you're given in the problem. I usually underline it, and that becomes what goes in the first box on the stoichiometry problem. You're going to cancel out everything using your unit analysis in the boxes. So this is when we do that large box thing with all the different boxes, and we cross out the units that are on the top and the bottom. And then this is going to be the only new thing here. All right, so steps 1 through 3 were just basic stoichiometry. Step 4 is we're going to have this delta H as a new conversion factor. So delta H is just going to give us a way of converting between a quantity of something and the energy that's absorbed or released. And as I said, I'll go through that in an assignment later on. So go ahead and check that out, and I think that should help. All right.